In our last tutorial, we looked at how to convert our TF model to a TF-Lite model. In this tutorial, we'll be taking it a step further and looking at the effects of optimization on our TF-Lite model. So before we start our tutorial, um, make sure to change your runtime type to GPU. This is because the model that we're training in this tutorial takes up a lot of RAM, um, and it could slow down your training. Okay. So as usual, import the necessary libraries. So just to set up the task that we're going to do, we're going to be dealing with a binary image classification problem. And the data set that we're going to be using is called the cats versus dogs data set. And as the name suggests, it has images of cats and dogs. So the first thing we're going to do is load our data set using the tfts.load function and into our train, validation, and test data sets. So we're going to be splitting it into these three subsets using our training data. So this data set has only a trained data. So as a result, we're going to be using the first 80% as our training data set, the next 10% as our validation data set, and the remaining 10% as our test data set. And we go ahead and print the number of examples. We see that we have around 23,262 data samples, and we have two classes. Okay, so next we're going to be visualizing our training examples. So we see that cat is corresponding to class 0 and dog is corresponding to class 1. But the thing that we should notice here is that all the images are of different sizes. So the first thing we're going to do is actually standardize this and resize all our images to 224 cross 224. So we define a user-defined function called format image that resizes each image to 224 cross 224, and we also normalize our images. So with our validation, train, and test data, we're going to batchify them. We define a batch size of 32. So we take our raw train data set, okay, and then we shuffle them. So the importance of shuffling in our training data set is that each time our model goes through all the images per epoch, we want to make sure that it's not learning any sort of pattern just because of the order of images. So each epoch, remember that each epoch goes through all your images in your training data. So we want to make sure that it's able to really generalize and not overfitting to the order of data samples within your training data set. So as a result, we shuffle the data set each epoch. On top of that, we have a map of format image. So map is actually, this is actually a Python syntax thing where you are applying the user-defined function format image to every sample in your training data. So map essentially helps you replace a for loop where you'd have to iterate through each training data sample and apply format image on them. So this just replaces that. Then we go ahead and batchify the training data set with our defined batch size. And finally, we have this command called prefetch of 1. This essentially is a TensorFlow optimization trick where once we are processing one batch, TensorFlow makes sure that it already is handling or getting your second batch of data ready. And this just improves latency. So that was our test batch. For validation batch, we go ahead and again apply our format image function to resize all images in our validation data set. We batchify it, and then we go ahead and apply this prefetch command. So we don't shuffle our validation data set because we are training only on our training data set. You don't really learn anything from your validation data set. And finally, for your test data, we again resize and normalize all our images. And we don't batchify our test data. We apply it one by one. So we just have uh, a batch of one. Okay. So you could possibly get a better idea of what train batches or the size of train batches by just printing the length of it. You get 582. So 582 is essentially 80% of 23,262, which is your training data, right? So the first 80%. So 80% of 23,262 and divide that by 32. So you have 582 batches. So that's the significance of 582. Next, so these train batches, validation batches, and test batches actually contain tuples of images, comma, labels, right? So when you write a for loop through it, you would have to do a tuple unpacking to get your image as well as your label separately. So that's what we do here. And if we didn't have this take one, this for loop would run 582 times because you're running yeah, running equivalent to the number of or the length of train batches, which is 582. If we do take one, we are just running the for loop once. So just for one batch. Okay. And we're just writing this for loop to get an idea of the size or the shape of our image batch. So when you print image batch dot shape, we see that we get 32 cross 2, 24 cross 2, 24 cross 3. So it's essentially one batch of 32 images. And each image is of size 224 cross 224, and 3 just signifies that it's a colored image. Okay, so now that we've got our data pre-processed and ready, let's define our model. So we are going to be using transfer learning here. So we're going to be using pre-trained weights of a model called the MobileNet V2. And this MobileNet V2 model has been trained on a data set called ImageNet. And ImageNet, it's a really popular data set that contains millions and millions of images uh, that span across multiple classes. Okay. And these data sets actually can be found on TensorFlow Hub. If you go to TensorFlow Hub, you can find multiple pre-trained weights that could be applicable for different applications. So this is something that you could do for your final project. So we define the model that we want, or the pre-trained or the base model that we want. We define the size or the pixel size of the inputs. And we also see that according to the documentation of our module, the output feature size is of size 1000 to 80, which essentially means that you have 1000 to 80 neurons at the last layer of this base model. Okay. Um, yeah, so that's this is our pre-trained model or our base model. And now we're going to be building upon this to fit our application. Question one, why do we use transfer learning? We use transfer learning because we're taking advantage of the fact that most of the initial layers for most applications learn features that are generalizable. So such as lines, corners, edges, etc. And by doing that, we actually cut down on training time and we can expect faster conversions. Okay. Now we define our entire model, which is essentially this base model that we defined above, plus a few layers that are customized to our application, which is the cats versus dogs application. And this whole thing becomes the complete model. Okay. So we define our feature extractor, which is our base model. We use the Keras layers API so that this pre-trained model is converted to Keras layers, which is what we're going to be using. So we have our module handle, which defines the MobileNet V2 model. We have the input shape +3 to specify that it's a colored image. Output shape trainable equal to false. So this is our feature extractor. And this should be familiar to you guys. So we have our tf.keras.sequential. We have the first feature extractor, which we define over here. followed by one dense layer with number of classes, which is 2. And we define our activation. So here we've just defined one additional layer to fit our application, but generally you would maybe put a few more layers to define um, your complete model. Okay. So now this model is the model that we need to train. Question 2, can you think of why we set the trainable parameters as false for the pre-trained model? So by setting trainable equal to false, what we're saying is that all the layers or all the parameters of this feature extractor or our base model should not be modified. So this allows us to converge faster. And the only parameters that we should be training or updating are of this last layer that's corresponding to our custom application. So you could so trainable equal to false means that the initial base layer will not be updated. You could set it to true, and it would definitely take more longer to train, but it could improve accuracy. But remember that even if we are training all the parameters in this feature extractor, we are starting from good initial weights. We aren't starting from random weights. So we could still expect our model to converge faster during training. So this is just a summary of our model. This is our feature extractor layer and then finally our output layer. And we see that the number of trainable parameters is 25, around 2500, which corresponds only to our last layer, and non-trainable parameters is everything else. Next, we define our loss function, the cross entropy function, and we also define our optimizer as Adam. And then we go ahead and compile our model. Next, we train our model using model.fit. We train it on our train batches, and also our validation data will be equivalent to our validation batches. We train it for only around 5 epochs because we see that our train or our base model was really good, and we were able to achieve an accuracy of 99 on our test data and 98, actually close to 99 on our validation data set. Next, we go ahead and save this TensorFlow model using tf.save model.save. So everything we've done so far is pre-process our data set, define our model, and train and create our TensorFlow model. Next, we're going to convert this TensorFlow model to a TF-Lite model. So model 1 is our basic TF-Lite model. We take our cats versus dogs save model. We use converter.convert and convert it to a TF-Lite model. This is saved as model1.tflite. And we see that this model is around 9 MB in size. So next thing we're going to do is actually apply some post-training quantization. And there are 2 different things that we're going to look at. One is dynamic range quantization, and the other is integer quantization. So in dynamic range quantization, we again start with our TensorFlow model, and we use the converter.convert function to convert it to a TF-Lite model. But we also set this flag, which brings about this dynamic range quantization, where our weights are now converted from float 32 to int 8. Okay, so all our weights are now represented using int 8 numbers. And when we use our write bytes API to save our model.2, so it's model2.tflite, we see that our model is actually 4x smaller than our model 1. So essentially with some post-training quantization, where we represent now 32-bit numbers, 32-bit weights as 8-bit weights, we get a 4x reduction in size. Now, model 3 is with integer quantization. So in addition to our weights being quantized, we also quantize our intermediate neuron outputs or our activations, essentially. So they are also now represented using 8-bit integers. Now, in addition to now how we bring about that is in addition to setting that flag that we did above, we also create a representative data generator. Now, the purpose of this is that the idea behind integer quantization is that weights always when you train a model, now you don't change a model, right? So you've trained your model, and the weights that you have now don't change. They've already converged to the optimal value. But your intermediate outputs can change based on the inputs that you give into your model. So we use this representative data generator to go over a subset of our test data or our test input data and get an idea of the range of values that our activations or our intermediate outputs can take. So getting an idea of a range will help them sort of do some pre-quantization such that we can reduce we can bring about more quantization, essentially. Okay, so that's what this representative data generator is for. We use converter.convert again and save this model as model3.tflite. We see that the size again is around 4x smaller than our initial TF-Lite model 1. Okay, so just a quick recap. Model 2 has the same TF-Lite model, but with dynamic range quantization. That's brought about by this flag setting. And here the weights are quantized from flow32 to int8. In TF-Lite model with integer quantization, which is our model 3, in addition to our weights being quantized, we also quantize our intermediate outputs or activations, and that's brought about by including this representative data generator. And both model 2 and model 3 are around 4x smaller in size than model 1. Now, finally, we have these three models. We're going to run some inference. Like we saw before, we're going to be using the interpreter to be able to do so. So we instantiate our interpreter, we allocate tensors, and then we set and get the input and output. And we run through all our test data. Over here, we run through 100 test data samples. We get our prediction. We already have our test labels, which are ground truth. And we check whether they're equal or not. And if they are equal, then we improve our score by 1. If they're not, we don't. And that's essentially sort of telling you out of 100 predictions, I got 100 correct. So for model 1.tflite, which is our base model, I fed in 100 test samples and I predicted all of them, or our model 1, predicted all of them correctly. So this cell essentially does your inference. So you can change this from model 1 to model 2 and model 3 and determine whether you still get all 100 correct or you get a few lesser correct. And yeah, also, so for question 3 and question 4, what you need to do is again, run all three, see how many predictions you get right, and also note down the time. So the iterations per second for each of the 3 different models. So we've run inference, and we can also visualize our predictions. So this visualization cell essentially just takes in your predictions and plots the images, but also as like a green tag whether it's predicted correctly, or as a red tag if the prediction was wrong. And it also predicts a sort of confidence value along with your prediction. So in this inference, I got 100 correct. So we probably would not see any red, but you can see the percentage slightly differing. So all of this is 100%. Let's see. Okay. Yeah, I guess this was 99%. I was slightly confused, uh, but it predicted it correctly anyway. This one was only 95% confident. This was 94% confident. This was 99% confident. Yeah, so along with whether it was predicted correctly or not, it also predicts a confidence percentage um, based on whether your predictions were very close. For example, it could have predicted 55% cat and 45% dog. Um, but it still predicted it correctly, but it was not as confident. And yeah, so you could again run this inference for model 1, model 2, model 3, and then visualize them individually and see whether you are able to get all of them correct or not.